Thanks for tuning into this episode of QRP to QRO. This is video number 10, how to use an oscilloscope to monitor DC amperage. My name is Steve. My amateur radio call sign is KC8QVO. If you've paid attention to some of my videos, I'm starting a series on portable power systems. That's the topic in video number 9. That's my introduction video to the series. And if you go in there, there's a PowerPoint presentation that covers a lot of the various subjects that I'm hoping to cover. And one of the topics, one of the main points about the portable power systems is that of solar power and batteries. And I was trying to come up with a better method of measuring amperage and wattage instead of just using a meter, such as one of these little guys, or a more conventional handheld multimeter. And I thought an oscilloscope would be a nifty way of doing it, plus you get to see the graph as well. And this video is just a quick tutorial on how I've got that set up here. So as we get into the schematic, I am using a screen recording software. So if you see my mouse cursor, I'm going to use that as a pointer as we go along. Over on the left side is the power supply. You'll note the positive and negative leads. Moving down, we get to the load. Again, positive and negative leads. And then over on the right side, we have the oscilloscope listed. And there's channel 1 and channel 2. Now the method that I'm implementing here is that of a shunt resistor. That's listed here by R shunt. And you'll see the long resistor in the middle there. Now if you think about a normal meter that uses a shunt for monitoring amperage, that shunt is typically placed on the negative lead. So I'll pause here for a minute because the reason that this is on the positive side has to do with the way the grounding is on the oscilloscope and the power supply. So if we think about this for a minute, both the power supply and the oscilloscope, if they're plugged into the same outlet and in the same power circuit, they're connected together. So let's look at that deeper here. Each one of the probes has a ground lead. There's one on channel 1 and one on channel 2. To measure voltage across a device, in this case the shunt resistor, the tips of those probes, or the positive side if you will, is what we're measuring that difference in voltage of. Both the ground leads of each probe are at the same potential as the chassis of the oscilloscope, and also at the same potential as the chassis or the negative side of the power supply. So if we take this shunt and place it over on the negative side, again keeping in mind to measure the voltage across a device, we need the tip of the probe doing the measuring, not the ground leads. Then what we need to do is, instead of having this ground bus that I have in the middle that's noted by this ground symbol, if we place the shunt over on the negative side, then this bus needs to be raised above that negative voltage to positive voltage. So with the systems that we're working with here, it's 13 or 14 volts DC. So if, again, we place that shunt over on the negative side, then this bus is then raised to that 13 or 14 volts positive. So if we connect it up without changing anything in how we're powering either of the power supply or the oscilloscope, then what we end up doing is shorting out the power supply because it's backfeeding through the ground, through the oscilloscope chassis, out the power cable back to the power supply. So that's not a good thing. The other issue is if we get around that by, okay, so let's say the shunt is negative voltage and the bus is positive, why not just flip around the probe so the ground of the probe is connected to the shunt on both sides, and the tips, or the positive side of the probes, are connected to the bus. Then what is doing the measuring, again with the oscilloscope, any way you slice it, what's doing the measuring on the oscilloscope is that tip of the probe, or the positive side. which is connected to now, in this example, the positive power bus. And then the ground is what is connected to the shunt. We can't do that because by using that method, the positive, or the voltage going through that negative side back to the oscilloscope is bypassing the resistance of that shunt, and you're going to get a constant voltage on both channels 1 and channels 2. We don't want a constant voltage, we want to monitor the voltage difference. So again, going back to the power supplies to both the main power supply over here and the oscilloscope, the way that you could get around that ground issue and the short circuiting is if you float the power supply to the oscilloscope. And I did play around with that. I added a power inverter to another power supply. So power inverter, it goes from DC, so 12 or 13 volts DC, to 110 volts AC. And by floating the power supply to the oscilloscope, that allowed me to bring the ground potential up to that 14 volts of the other circuit, because they're two totally different circuits at that point, hence the term floating. The circuit that the oscilloscope is operating on, including the power going into it, is totally separate and isolated from the power supply to the main power supply that is supplying the power that we're trying to monitor on the oscilloscope. So that gets a little bit complicated. So again, by placing that shunt resistor on the positive side, in this case, it makes things a lot easier to line up and keep track of. So that having been said, we'll move on to the components here. You'll notice I have two capacitors. They're C1 and C2. They're both 4.7 microfarad, 25 volt polarized electrolytic capacitors. And the reason I have those here is because they filter out ripple in the measurement going back to the oscilloscope. And I've got a screenshot I'll show here in a minute of what it looks like without those there and what it looks like with them in place. So the key to the value of the capacitors is we want those to be big enough that they filter out that ripple, but they're not so big so as to mess up the voltage measurement. So again, we're dealing with millivolts in the reading that's going back to the oscilloscope. So if we have too large of capacitance, then that time delay in the voltage changing within the capacitor is going to throw off the measurement going back to the oscilloscope. So we don't want that. We just want a smoother reading going back to the oscilloscope. So we just want to take off that ripple and not adjust that voltage measurement a whole lot. As far as the shunt resistance, the value depends on the current. So in my case, with what I've been measuring here, has been between 200 milliamps and 2 amps. And the resistance that has been working with that for me is 500 to 700 milliohms. Again, that's milliohms, not megohms. So this would be 0.5 to 0.7 of an ohm, very low resistance. Now, if you get into higher amounts of current, well, I'll back up a second. So the higher this resistance is, the larger the voltage drop across that with any same given current draw. So if you put, say, 750 milliamps through a 500 milliohm shunt resistor versus 750 milliamps through a 2.5 ohm shunt resistor, then the 2.5 ohm resistor is going to have a higher reflected voltage drop across that. So one thing to keep in mind with the higher the resistance also is you're going to get a lot more power loss or dissipated energy within that resistance. So the key to what resistance you pick and what material, we'll get into that in a minute, is you want enough voltage drop across that resistance to be able to measure on the oscilloscope, but you don't want so much resistance so as to cause a lot of power loss in that circuit. And going back to the material to pick, whether it's wire or a foil sheet, a strap of some kind, etc., you want something that is going to handle the amount of current that you're putting through it without overheating and melting. And you'll see that here when we get into the spreadsheets and the graphs I have. So with that having been said, let's move on to the rest of the system here. So this is the circuit, and again this probe here is channel 1, that's noted by the yellow band, and we have the ground side of it connected to the main ground bus that's in the back here. And then over on this side we have channel 2, which is noted by the blue band, and that corresponds to the traces that you'll see on the oscilloscope here in a minute. And then this coil wire, the steel wire, is the shunt. That's 28 or 30 gauge picture hanging wire. And then here's our two capacitors, the 4.7 microfarad electrolytics. So again, one on the input, one on the output. And I did add a third capacitor just for experimental sake on the output side, because I have another meter, the multimeter here. I was monitoring the output voltage so I could see what the input was versus the output. You'll see that here in a minute with the spreadsheets and the graphs in a bit. This is a dump load that I made. So I used that same picture hanging wire. Again, it's 28 or 30 gauge steel, and depending on where I have this tapped, depends on how many turns are in the circuit, and thus how much of a load is placed on the circuit. So the longer it is, the more resistance, the less load there's going to be, and the shorter it is, or the less amount of turns, the lower the resistance and the more current and the more draw on the circuit. See if I can angle that a little bit better. This set of coils is 34 gauge magnet wire. It's really tiny stuff, but that's another dump load that I was playing around with to get some other current values. But the one that I did use for the spreadsheets in a minute has all been done on this load here. And again, just depending on how many turns you tap, the shorter the amount of turns, the more current is dissipated. So let's take a look at the oscilloscope now. Again, the yellow line is representative of channel 1, that's our input. Blue is channel 2, that's our output. Again, the same color coding that goes back to the probes on the circuit a minute ago. And then we have the math scale set up here. So we're set to do the math function as a difference or subtraction. So source A is channel 1, source B is channel 2. And then all the scales we have reading in 500 millivolt per division. That's the vertical scale, 500 millivolt per division increments, both for the channels and the math scale. So I'll speed this up a little bit so you can see this. Let's see, we'll keep it on 100 milliseconds just to keep that rolling through. So what I've done is I've set the two cursors up. So you'll see them here down on the bottom. We've got them set to the math function as the source. And I'll change cursor B for a second. That's the one on the bottom. But you'll see that down here adjusting as I'm moving this up and down. And what we want to do is get that cursor down onto the trace of the math scale, because at the moment we have no draw on the system. So this is our 0 point. And then what we're going to watch is this box on the top that shows the position of cursor B and cursor A. B is on the top, A is on the bottom. And then the difference is really what we need to pay attention to, the delta V, or the difference between the two cursors. So if we switch this back to cursor A, you'll see that top line is moving now. So what I'm going to do is I'm going to use the K2 as our load. So it's off now, and then when I turn this on, watch this baseline here, you'll see that jump up just a tick. So there we're on. So if we take cursor A and scroll that down to where that math trace is now, so there we're right about in the middle of that trace. As the K2 is on and receive only, our delta V is 140 millivolts. So that's the number that we want to keep in mind. I've got a power level on the K2 set to 1 watt, and I'll go ahead and key that. We're using a dummy load to run into. This isn't going out an antenna. I'll go ahead and key that up here on the next go around. There we go. Oops, missed it. There we go. So now you can see that jump in our trace. And just so we can measure that, I'll go ahead and stop this. Go ahead and take this off of transmit. And then we'll adjust cursor B up to where that trace is on the math scale. And we want it right about in the middle of the trace. So there, now we're looking at a delta V of 520 millivolts, so it's gone up a bit. So we'll take the power level on the K2 up to say 3.5 watts. So that being a higher power level, we should get even higher voltage on the difference here. So we'll start this back up. And again, it's on and receive only, so we're up just a tick from the baseline. If we key this on, there's our jump up to the next power level. We'll freeze that, turn the K2 off. Then now, if we go in and adjust cursor B up to that trace where the math scale is, or the math reading, we're getting 820 millivolts. So you can see how that math scale is now being representative of the amount of current that's being drawn from the system. So let's get into, actually I tell you what, let me do one more run. I'm going to slow this way down. Let's bump this up to say a 10-second time base. So we'll let that run for a couple seconds, maybe up to that first division. But you'll see, again, cursor A is on the bottom, and there's our trace for the math scale, so it's right at 0. When it hits that next tick, we'll turn on the K2. There we go. So now we'll see that first step in the voltage reading. We'll let that go over another division, and I'll bounce this back to 1 watt of power. At that second division, we'll turn it on, and we'll let that go to the next division, and then I'll turn it off here. And now we'll bump this up to 3.5 watts. And on that next division, we'll turn it on. There we go. And there, now we're back up to that cursor B that we had marked before. So we'll go ahead and turn that off. Back to receive only. Then we'll turn the radio off. We'll stop it here so we can scan through the cursors one more time. Okay, there we go. So now we've got all our 3 different steps in there. Well, 4 if you include off. So we'll start at the first one again. There's our receive only, so powered on and receiving. And there we're right back up to 140 millivolts. We go to transmitting at 1 watt carrier. We're looking about, bounce that down 1, that's 580 millivolts. Then we go to the highest step, which was the 3.5 watt carrier. We're looking at 840 millivolts. And again, all we're doing is measuring the difference in voltage between channel 1 and channel 2, and then displaying that with that math function as the difference in the pink scale. So there we're set up to subtraction mode, and again, source A is channel 1, source B is channel 2. So not a whole lot to it. So moving on to a couple of screenshots. This first one here is of the circuit running without the capacitors. So if you notice, all the traces, again, the yellow and blue are channels 1 and 2 respectively. And then you have the math function in pink. That is the difference between those two. So if you look and see how fuzzy they are, again, that's that ripple or the change in voltage that's fluctuating very quickly through that circuit without the capacitors. So once we add the capacitors in, then all of the traces get noticeably cleaner. And that's the whole idea of putting the capacitor, both two of them, one on the input and one on the output of the shunt in this circuit. So you can see how much of a difference that makes here. So of course this method of monitoring amperage is not perfect. So let's get into the numbers and dig a little bit deeper into the power calculations and more so the losses and efficiency in this particular method. So in the top here is a section where I was experimenting early on with this method, but the data I'm using in the graphs that I'll show here in a second start with the data here in the box. That's the main data that I collected. So what I did is I set the power on the main power supply, the Astron. I set that to 14 volts, and then I loaded that circuit. Again, you can check the notes here as to what that particular load was. Mark down what the voltage drop was, which is the difference between the cursors on the math function on the oscilloscope. So with each, and this is in volts, so that's 140 millivolts, 480 millivolts, etc. So with each drop in voltage, I took also a current reading. With that panel mount meter, it shows both voltage and current. So I took the current reading from that, and then I computed what the resistance was. Again, so the voltage drop is known from the oscilloscope. The voltage in is known from the panel meter going into the circuit, and the current is also known from that same panel meter. So these three sets of known values are what gave me the resistance values here. So another way to think of that is the resistance is the slope of the line representative of the voltage drop and the current. So moving down here, that's what I marked out here was the average between a couple of different sections. So again, as I mentioned, the current range that I'm most concerned with is between, say, 200 milliamps and 2 amps. So if you look at the chart here, with the K2 at 9 watts, we're just over 2 amps. And I did do one with the K2 set to 10 watts as well, but with the voltage drop, it was actually identical with the voltage drop on the oscilloscope versus the current that was measured. So I decided to take that out of the the graph, because it's skewing the data, in other words. So, again, going back to the current that I'm trying to work with, it's between this 200 milliamp and 2 amp current range. So what I did is I took an average of that, so 2 amps and under, or about 2 amps and under, and then I did another one of the higher amperages here. So that's figure about 2.5 to 3.5. So I came up with an average slope between those higher currents, and then I did all three, or I should say both of them combined. So I took the whole current that I worked with from that, say, 200 milliamps up to that little over 3 amps that you see here, and that gave me this all-up slope, which I put the resistance, or the apparent resistance, that matches that slope, because again the resistance in this case is a function of that average slope of whatever particular line that is. So let's move into the charts here. Let me shrink the zoom a little bit so we can get that to all fit in the screen. So this first one is the voltage drop versus current as measured between the current being the panel meter, and the voltage drop is, again, the difference on the oscilloscope between the cursors using the math function. So that's what we're looking at there. And then I've expanded that out, and looking at the blue trace, again, that's the same exact data set that was on the graph before. So that's our measured data points. And then what I did is I overlaid 3 different slopes on top of that, again going back to those averages. So one average being that 2 amps and under, another one being 2.5 amps and over, and then both of those combined for an all-up representative slope of the whole data set. So let's look at that again a little bit closer. So what you see is, again, the blue trace is the actual measured data points, and that's fairly consistent all the way up until you get to that 2 amp point, and then over 2 amps we start getting some fluctuation in that slope. And again, the slope of each line is a representation of the resistance of that shunt resistor. So if we look at that here, 2 amps and under, we're looking at 572. That's, again, milliohms, not megohms. 2.5 amps and over, that's the yellow line, so that's the highest slope there is. That also shows as the highest resistance being 688 milliohms. And then if we factor all of the data points combined, our average resistance comes to 597 milliohms. So again, if we look at this chart and we block it off there at the 2 amp range, then everything below that is fairly consistent. There's not a whole lot of variation in that slope. However, once you get above that 2 amp range, then we start getting some fluctuation in that, and that is due to the higher current heating up that shunt resistor. And again, it's picture hanging wire, just thin steel wire. So again, the higher you pull current through that wire, the hotter it's going to get, and you're going to see this fluctuation in that current. So let's take a look at the heating aspect of that wire, because of course, if a device is getting hot, that's lost power. That's a given. That heat doesn't just generate from itself. That has to come from some energy. And we can see that here in this data set below. So again, the same 14 volt input or thereabouts with all these data points. Some are a little bit lower. There's 13.9 and one that's 14.05. But what I did here was ran the same test of the current draw between the K2 and the dump loads that I showed you. And I came up with the current off of that panel meter. So again, these are all known values, and then everything on this side was just computed from all of these values here. So I took the difference between the output voltage and the input voltage, whatever that voltage drop was, I factored that in with the current and came up with all the power values that you see here. So there's the dissipated power, meaning the lost power. There's the load consumed power, meaning how much the load is actually drawing, and then both of them combined. So the total power dissipated, which of course is the total current at the input voltage. And then from these values, I calculated the percent lost power. So this is how much power in percent that we're losing with this particular method at these particular voltages and currents with the particular shunt material and resistance value that I'm using. So let's take a look at that on the graph. So here's a visual representation of that data set. And again, if you consider current being one value through that whole circuit, and there not being any deviation in that, it would make sense then that our total power in wattage would be a straight line, and that's what we see represented here in the green. The dissipated power, or the power that's lost in wattage, is representative by the orange trace. The consumed power by the device, or in this case the dump load I'm using, is representative of this yellow line. And then again, the percent of lost power, not the wattage, but the actual percentage, is represented in the blue line here. So we can see it's not, again, going back to the percentage, if that was a constant value throughout the range of currents that we're using in this setup, then that percent should be flat all the way across. It should be one value. But of course it's not. So the higher the power draw through this particular system, then the higher the amount of loss that we have in that, because again, that wire is heating up, and that heat has to be generated from something, and that's the lost power in the circuit, which again is a relationship between the voltage drop that we see on that oscilloscope that we're measuring across the shunt resistor. So again, you're not getting something for nothing here by that voltage drop, which is an indication of power loss also in that circuit. We're also gaining the information that voltage drop is giving us in that correlating to an amperage that we can use for whatever purposes we're trying to measure. So again, it's not an absolutely perfect measurement, and hopefully this gives you an illustration of how you can also factor in what the losses are, so you can recalibrate what those readings are to come back to a more accurate amperage reading with whatever measurement that you're trying to make. Let's take a more detailed look at the amperage in that above 2 amp range with this particular shunt setup. This is about 2.5 minutes worth of time with an amperage between 3 and 3.5 amps, I believe. But what I want to point out first off is, again, channel 1 is yellow. That's the input of the circuit. And channel 2 is the blue trace, or the output of the circuit. So if you see channel 1, the yellow in the background there, it's fairly smooth and flat all the way across. And then you look at channel 2, or the blue trace on the bottom, and it seems to fluctuate and meander all over the place. Now again, this is the scale is set to 10 seconds per division, so the reading that we're looking at is about 2.5 minutes long. But what it also does a really good job of describing pictorially is the detail that you can see in the response to this particular measurement. So yes, the shunt performance does dwindle once you get above that 2 amp range with the particular setup that I have here. But what's also important in going back to why this particular type of measurement using an oscilloscope to monitor the amperage is good is you can see a level of detail in this particular type of graph that you'll never be able to see with any LCD meter that just shows you a number. So if we expanded that out, we could even go out to, I believe, 50 seconds per division is the widest this scope goes. But if you can expand that out and you can monitor this over a period of time, this will give you a visual representation that you just can't get with any other LCD type numerical measurement. There are probes that you can buy commercially made that are for monitoring DC amperage with an oscilloscope. However, they can cost anywhere from several $100s to several $1,000s. So although they do exist, they're an expensive option, whereas with a couple of capacitors and some spare wire from your junk box, you can make a sampling board such as this that will give you some respectable results. Of course, you have to factor in the losses and inefficiencies, but when you compare what you can see with the detail on an oscilloscope screen versus just a numerical readout on a meter or a multimeter, you can get amazing detail in results that otherwise you'd never be able to see. So I hope you found this video informative. Again, it was a little bit on the long side, but there was a lot to cover. My name is Steve. My amateur radio call sign is KC8QVO, and this has been video number 10, how to monitor DC amperage with an oscilloscope. Stay tuned to my video series on portable power systems also, starting with video number 9. That's my introduction video, and again, there's a PowerPoint presentation in there that'll give you some more depth to some of the subjects I hope to cover within that. So if you found this video informative, helpful, or it's encouraged you to experiment with electronics, etc., hit that subscribe button underneath the bottom right of the screen and tap the bell icon for notifications, so that way you'll get an alert the next time I post a video. You can also follow me on Twitter at QRP2QRO, and YouTuber's famous last words, stay tuned.